All right, let's jump right into this explainer. Today, we're tracing the absolute staggering evolution of 3D printing. I mean, we're going from accessible desktop tools all the way to the mind-bending frontiers of manufacturing, biology, and actual lunar bases. Additive manufacturing has completely rewritten the rules of what human beings can build, and right now we're going to break down exactly how it does that.
We're basically climbing a technological ladder today, moving through 5 distinct tiers. We've got desktop plastics, industrial powder, heavy metal manufacturing, multi-material magic, and finally, printing the future. We'll look at the machines, the incredible materials they use, and the specific problems they're solving across all sorts of industries. Let's hit it.
Starting right at the foundation, here is Section 1, Desktop Plastics, looking at FDM and Resin. These are the machines you can literally fit right on your desk at home.
Now, Fused Deposition Modeling, or FDM. I know it sounds super intimidating, right? But honestly, FDM is essentially just a highly precise hot glue gun mounted on a moving mechanical frame. It operates exactly how a 5-year-old would invent manufacturing. You just take a solid stick of plastic, melt it, and squirt it exactly where you want it. That is the whole secret.
Basically, the software tells the machine to heat a nozzle up to somewhere between 180 and 260 degrees Celsius. It squirts a tiny, precise line of molten plastic, drops the build plate a fraction of a millimeter, and then, well, repeats that process about 10,000 times. It builds up kind of like a very slow, deliberate breakfast stack made of plastics like PLA or ABS. And just like that, customized brackets, engineering test pieces, or even cosplay props are brought into existence for hobbyists and engineers.
And honestly, here's the absolute miracle of democratized manufacturing. You can get started with a basic Bamboo Lab A1 Mini or, a used Ender 3 for just $150. It's an incredibly accessible entry point if you just want to hold something in your hands that you designed on a screen a few hours ago.
But FDM definitely has its limits. Mainly, it leaves visible layer lines. So if you want to print, say, a tiny 28mm miniature knight with a flowing cloak and individual chain links in its armor, you've got to move away from melting plastic and look at Chuck Hull's 1986 invention of resin printing. This process literally pulls solid objects out of a vat of UV-sensitive liquid syrup using focused light. It's wild to watch.
So the crucial point here is extreme precision. Modern MSLA printers use LCD screens to flash entire layers of UV light all at once. And this level of precision is exactly why certified dental MSLA printers can take a patient's turnaround time for things like clear aligner molds or surgical guides and drop it from a grueling 2-week wait at an external lab down to just 8 hours in-house. It's a total restructuring of the patient experience. Way less time just sitting in a dentist chair waiting for a fix.
However, I've got to warn you, you have to be ready for the hidden costs. We're talking fit replacement films, gallons of isopropyl alcohol for washing, and a distinct odor that is probably best described as chemistry homework gone wrong. It's a process that absolutely requires a good mask, serious ventilation, and honestly, a very understanding roommate.
Okay, let's move up to our next tier. Section 2, Industrial Powder, specifically focusing on SLS printing. This is where we leave the desktop behind. These machines are massive.
Now think about this. When you're printing complex internal channels or interlocking assemblies on a standard desktop printer, you always need disposable support structures to hold up the overhanging parts, right? Otherwise they just droop. So with industrial powder printing, you might be wondering, how do the overhangs not just collapse into empty space?
Well, the answer is genuinely beautiful. Selective laser sintering, or SLS, prints directly inside a bed of nylon powder. A laser passes over a flat layer and sinters the particles. It essentially fuses them together without completely liquefying them. And because the part is buried in that bed, the surrounding warm, unfused powder acts as the automatic support. You literally just dig your finalized functional part right out of the powder block. This opens up geometries that are completely impossible to tool conventionally. It's exactly why you see SLS used for functional, load-bearing parts, like Additive running midsoles or weight-saving aerospace brackets.
Now, the capability to completely skip the injection mold house, which saves weeks of waiting and thousands of dollars in tooling, and just iterate your functional design overnight, yeah, that comes at a steep price. An entry-level Formlabs machine starts at around 19 grand, and heavy industrial systems will easily run you well into the 6 figures.
All right, moving from plastic powders, we escalate to Section 3, Heavy Metal Manufacturing. And let me be clear, this isn't just printing a plastic part and giving it a shiny chrome finish. We are talking about serious structural metallurgy here.
Welcome to the territory where the machine itself is a $300,000 infrastructure investment. And the raw material? The metal powder, whether that's titanium, steel, or Inconel, costs up to $400 per kilogram. It's intense.
Look at how this breaks down. On one side, you have companies like SpaceX and Stryker using direct metal laser sintering, or DMLS. They literally melt titanium into rocket injectors and porous spine implants, creating impossible geometries like internal cooling channels that curve perfectly with the shape of the part. But then, on the other hand, automotive suppliers are taking a totally different route. They're evaluating binder jetting. This dramatically speeds things up by using multiple inkjet heads to spray an organic glue right onto metal sand, which is then sintered in a massive furnace. It's a game changer, and it's the technology poised to bring additive manufacturing up to true mass production speeds.
Next up, we enter Section 4, Multi-Material Magic. We are stepping into the realm of product design sorcery with PolyJet technology. This is where prototyping becomes, essentially, near-perfect simulation. So, instead of a giant powder bed or a vat of liquid, PolyJet acts a bit like a highly advanced, standard inkjet printer. It drops liquid photopolymer from multiple heads and cures it instantly with a UV lamp. And get this, it layers this material at a staggering 14 microns. To put that into perspective, that is far, far thinner than a human hair.
And this brilliantly illustrates why product designers and medical professionals absolutely rely on it. You can print using up to 7 materials simultaneously. In one single print shop, you can create an object that transitions seamlessly from a rigid plastic chassis right into a perfectly clear, transparent window, and then into a soft, flexible rubber grip. Companies like Nike use it for footwear prototypes, and cardiac surgeons use it to print exact, multi-density replicas of a patient's heart. They literally rehearse complex procedures on these models before they ever make a real incision.
Now, the resins do degrade over time, and the top-tier Stratasys machines that pull off this magic cost around $500,000. But the ability to hold a perfect, multi-material prototype in your hands, compressing the flexible rubber elements and seeing right through the transparent ones, all without commissioning a single piece of factory tooling, it is a total paradigm shift for product development. And finally, we reach our fifth and final tier, Section 5, Printing the Future. We are stepping completely out of traditional manufacturing here and diving straight into applied science fiction. This is where 3D printing actually starts reshaping life and society.
The applications here are just staggering. On the micro scale, we've got bioprinting. We're talking about extruding hydrogels loaded with actual living cells. We're seeing companies like Organovo print hepatic liver tissue constructs for pharmaceutical testing, and the Wake Forest Institute is literally producing functional bladder scaffolds. Then you flip to the macro scale, and we have construction 3D printing. Icon's massive Vulcan printer is out there extruding proprietary concrete to build entire sub-500K single-family homes down in Austin, Texas. Oh, and they're also testing lunar regolith structures for NASA. Whether it's printing functional tissue to help solve organ donor shortages or printing a habitat on the moon, the unifying principle is exactly the same: precise layer-by-layer material deposition.
If you wanted to go out and own every single piece of technology we just covered in this explainer today, the total cost would be, well, staggering. As our source perfectly puts it, it would cost approximately the GDP of a small island nation. But, no one operating at this frontier is really asking what the machine costs. The value of rewriting the rules of human reality, biology, and infrastructure, that is absolutely limitless.
We've seen how depositing material precisely, layer by layer, has completely revolutionized our world. We've gone from printing little plastic trinkets on a desk to metal rocket engines and actual beating biological tissue. So if we can print living tissue and lunar bases today, it leaves us with one massive, thrilling question to chew on. What previously impossible thing will human beings deposit into existence next?